All right. All your grades have been updated on Blackboard. So you can look at Blackboard and see your final grades as of now, or as of last Thursday, I should say. So we're going to move into chapter 10 this week. And we're going to start looking at intervals. So one of the things that we've been talking about for a while is how we can take a value that we get from our samples and use that to start drawing conclusions about our general population. So we've, like I said, I've talked about it, given examples about it, but now we're actually going to start seeing those calculations and how we actually can do it. The nice thing about chapters 10 and 11, for the most part, there's nothing new. Like, it's just adding on like a step or how we're going to look at something that we've already done. So we're still going to be using the z-tables. On Wednesday, we're going to talk about actually what's known as a t-table, but the concept and how we're going to use it is the exact same. It's just a different set of numbers because we don't know something. So we're going to start looking at the statistical, and we're going to look at being able to determine what is happening out in the world and not just what's happening in our sample. So the first thing we want to look at is what's an estimator. So when we're looking at the different values, there's three different things that we're going to look at. And actually, we're only going to actually do two of these. We're not going to do the standard deviation one. So the first one is the x-bar. That is our sample mean. And we use that to estimate the population mean. So those both are mean. This is just sample, and then that's the population. And then we have p hat, which is our proportion. And that is we're going to be estimating the proportion of our general population with that sample. And the last one is standard deviation, which we will not be looking at. I'll leave the chi-squared formulas for higher level stats class. Okay. So we've talked about the means, we've talked about proportions, we've done a bunch of problems and calculations and stuff for them. So that stuff's still going to be useful for this. And you don't need any of that. All right, what's that? Huh? A normal curve or a bell curve, right? So our mean is in the middle. On the middle, that's our mean. Our negative side and our positive side. Does it ever get to 0? No. So when we're looking at our calculations, we're going to look at this. So in essence, what we're going to be talking about is that's my sample mean in the middle. And we're going to figure out where our population is going to be somewhere spread around it. The key is where is it going to be spread around? How far are we going to be looking at either side? So when we originally looked at this way back, I think it was in chapter 3, we did the empirical rule. Remember, we had the 68% one standard deviation, 95% two standard deviations, and 99.73 standard deviations. Well, that's actually what we're going to start looking at today with this. So we're looking at one standard deviation, we're looking at in here. So if my mean is in the middle, one standard deviation away from that means that there's a 68% chance that my answer is going to be somewhere in between there. If we go out to 2 standard deviations, there's a 95% chance that my answer is going to be somewhere in between those two values. Does that make sense? Okay. So if I told you there was a 95% chance that you were going to win the lottery, would you play it? If I told you there was a 68% chance that you're going to win the lottery, would you play it? You have to start thinking about it a little more. Still over 50%, but you have to start thinking about it. So when we're talking about actually having the answer basically within that. That's what we're talking about. Like, that's how confident I am in that my answer is going to be in there. All right. So within 2 standard deviations, I'm 95% confident that I have the right answer. Is it 100%? No, it's 95%. Right. It's not 100%. And that's actually very, very, very important. Okay. So whenever you're looking at any type of statistics, even if we went out to the 99.7 at 3 standard deviations away, it's still not 100% guaranteed. Okay. It's close, but there's still a possibility that you're wrong. All right. So in all statistics, when you're looking at it, you still have that possibility that you're wrong. That can happen. Okay. And on the other side of it, you have to remember that when people are telling you statistics and stuff like that, or doing the data and the calculations, they could be wrong. That is a possibility. There is not 100% guarantee that it's going to be correct. All right. Everything is based on probability and stuff like in statistics. It's not always going to be a guarantee. All right. Probably one of the most important tables that you're going to write down, because you're going to use these numbers a lot. You can find all these on your Z table. It just takes you more work. So I'm going to say write these numbers down, because these are the numbers you're going to use most often. These are known as your critical values of Z. So depending on how confident you want to be in your answer, 80%, 90%, 95%, or 99%, those are the Z scores that we're going to use.
What letter is that? Is that like...
Oh, it's a small alpha. You don't have to necessarily, the symbol's not going to matter. You can put an A if you want. You can put whatever you want. The symbol's not going to be that important. A couple numbers I want you to key in on this one. Notice 95% is not 2. It's close, but it's not exactly 2. So the empirical rule where 95% of 2 standard deviations is close, but it wasn't exact. It's actually 1.96. The other one is 1.645. Do you remember hearing that number before in this class? So if you remember, when we were talking about 5% on both sides, and we were finding it, you had a chance of, it was 1.64 or 1.65, and I said we split it right in the middle. That's why. That is a number that we're going to use quite often. So 90% is 1.645, and 99% is 2.575. So those are the ones we're going to use most often. 80% is not used as often. It's typically 90, 95, or 99%. And a lot of that has to do with what we're looking at and how important what we're looking at is. I'm sure everybody's got this written down. I am going to show you how to use Desmos, the calculator, today to do a lot of these calculations to make your life easier. So we good? We good? Okay. All right. Here's my formula. You do not necessarily have to write down like the using the A over the 2 and stuff like. You can just put Z. You'll be fine. So this is known as my confidence interval. So your confidence interval, you start off with your sample mean. So that is something you will calculate and you'll be given. You need to know the population standard deviation. On Wednesday, we're going to look at some problems where we don't know the population standard deviation, because that's actually one of those things that we might not know, but there's a little bit different calculations for it. We need to use a different table for it. And then we have the square root of n. That formula that you look at right there should be very similar. We did something basically just like that in chapter 9. We were dividing the standard deviation by the square root of n and multiplying it by the standard deviation. We were doing those types of calculations. This one, we're just going both directions. So that's where the plus or minus comes into play. In Desmos, you can type in formulas. Okay. So in Desmos, you can type in a formula. That's the scientific calculator, DSMOS. It's a free online calculator that anybody can use. This is honestly the best calculator that you can use, and you can download it to your phone. It's an app that works as well. You can just go to the website. The app and the website are identical. There's nothing different about them. You can type in the formula as you see there. So I just did x minus z parentheses s over the square root of n. That's basically the exact same formula you just wrote down. I just used symbols that were one letter instead of multiple letters. What that allows me to do is it allows me to just type in numbers for each of those and quickly change them. So you don't necessarily have to type in all the numbers into the calculator and then have to constantly type in the entire formula multiple times, which you're going to see is very helpful in the next problem. Yeah.
And I know you answered it, but
It's okay.
for the a divided by 2 part of the
Ignore it.
It's just not there.
Ignore it. Because that a divided by 2 is those numbers. So basically what that is that when you're looking at 95%, this side over here is 2.5%. This side over here is 2.5%. They're not 5 on each side. So 95%, if you subtract it from 1, you get 5%. Divided by 2 gives you the 2.5, which is what you'd look at the z table for. By giving you these numbers, you don't have to look at the z table for them. And since those are the ones you were almost always going to use, it saves you having to worry about that divide by 2 piece.
So when you put it in decimals, where you do. So you did x
Minus z.
Over s, where.
And then standard deviation, S, over the square root of n.
Then you did it as the opposite?
Yeah, because it's plus or minus.
Okay.
So you need them both. Because in essence, when we're looking at a confidence interval, we're going both directions. We're taking from the mean, we're going both directions up. All right, so let's look at a problem. All right, so a random sample of 100 car engines has a mean weight of 425 pounds. We want to construct a whole bunch of confidence intervals, just because I want to actually show you the concepts of them. For a population mean, if the standard deviation is population is 900, we need specific pieces of information. We need X. We need our Z, which is our confidence or our critical value. And that comes from our confidence interval. So that comes from whatever we're looking at here. We need our standard deviation. And we need our N. So in this problem, what's my mean? No.
Oh,
425. What's my standard deviation? 900. What's my sample size? 100. And my Z or my critical value is going to change depending on the problem that I'm looking at. So my first one, we're going to do our 80% one. So that means my Z is going to be what? 1.28. All right. Any questions on what I found for this so far? Everybody understand where I got all those numbers from? Yeah. So now we're going to go back to Desmos. We typed in this formula. I'm now just going to fill in the numbers here. So my X was 425. My Z was 1.26. Standard deviation was 900. And my N was 100. DSMOS.com.
Yeah, but it doesn't, it's not.
Scientific. So go to Math Tools, pick scientific
I
calculator.
did, but it's not giving me the letters. Do you have to put in the letters?
Yeah, you hit ABC. On the bottom, you click ABC. And you can type the
Okay.
letters in, or just use your keyboard. Yeah, you can just use your keyboard to type in. So notice, once I fill in those boxes, there's my 2 answers. Done. Don't have to actually do all the calculations for them out again. Okay. This works really well when you have a bunch of problems you have to do with this type of equation. You type the equation at once, and you've got it done.
And then you,
So type the formula in,
I have it. And then I hit what?
enter.
Mhm.
So go to another line,
Okay.
and then if you type, did you type them both in or just one? There's the minus and the positive one.
I just did X equals O equals M equals.
Okay, so then you put the numbers in there. Did you type in the formula like I have up here above? Like this. Did you type in this?
Hmm.
You have to type that in on another line. That's fine, just do it. The parentheses or the square root?
The parentheses I got, but like the S over.
So S divided by, use the slash key on your keyboard, right next to shift.
What?
And then divide, which is the slash key. So it's right next to the shift on the right side of your keyboard. And then you can use the square root button on the screen. Right on the bottom under A squared, there's a little check mark button.
I just don't know. Not computer literate.
Look at your screen.
Yeah.
Click on the button that looks like a square root symbol. Right here. That's the square root key.
Yeah, on my screen.
Oh, click main. Make sure you're on your main screen, not the ABC button, because you have a keyboard for that.
Oh, I see. Okay.
And then put the N. Okay. Now, if you type in your numbers into those X equals, Z equals, S equals, and N equals like you put in, you'll be fine. Okay. Bridget, we'll do it right after class. So my confidence interval is between, so that means my mean is somewhere between 311.6 and 538.4. Okay, that's what my mean is. I'm 80% confident my mean is between those two numbers. That's what that says. Okay, does that make sense? All right, so we've done our sample and we're 80%. So this one, basically what they did is they decided that by doing the sample, now I can determine what the entire population of all engines would weigh. Okay, that's what that's decided. So all engines weigh somewhere between 311 and 538. At least I'm 80% confident that that's true. Okay. But the actual mean weight is that value.
Can you go back to that screen?
I'm going to in a second. Now let's do 90%. So the nice thing about using Desmos to do this, everything's staying the same, right? Except for my Z. I'm going to now use the 90% one. What is my 90% for Z? So I change that to 1.645, and it gives me my next two answers. I don't have to go through and redo all those calculations again or retype the formula back in. It's all there. If I could save this and have it like, here's the link to use, I would, but you can't do that. So you have to actually type the formula in. This works for any formula, by the way. So like, even in your algebra classes, if you have to find a whole bunch of values for like one equation, you could type the equation and just change the x's. So it is quite a nice little feature. All right, so this is 90%. Copy this over, so say that one. So is 90% a wider interval or a smaller interval? So hold on, I'm gonna go back here. So this was my 80, 311 to 538, and my 90 is 276 to 573. So it's wider, right? Does that make sense? I am now 90% confident that my value is going to be somewhere between 276 and 573. All right. So it's got to be wider because I'm more confident in my answer is going to be somewhere between those. So the bigger my confidence interval is, the more confident I'm going to be in it, the bigger the interval's got to be. That makes sense? Okay. So here's them all. And then we're going to go back and I'm going to do a couple changes to things in a second. So as you can see, as my confidence interval gets bigger, my range gets bigger. Okay. So if the 425 I already know, that value changes. The 900 I already know. The only other thing that I could possibly change is my sample size. So the bigger the sample, this is one of the nice things about Desmos. If I go down here, and I'm going to change my sample. So instead of doing 100, let's do 1,000 engines. So my sample size was now 1,000. Now my interval is closer. So one of the options that we have, if we want a smaller interval, is we can increase the sample size. Okay. If you're going to weigh 100 engines, say it takes you 10 minutes to weigh an engine. All right. It's 1,000 minutes. Maybe take you a day to weigh 100 engines. If I'm going to weigh 1,000, now it's going to take me 10 days. If I weigh 100,000, now we're looking at 100 days. Long time, right? But my interval is getting smaller. So now the piece comes into play is, where's that line? How accurate do you get it compared to how much time and money you're going to spend and energy you're going to spend to get it there? Okay. So while 10,000 makes a very nice range, it might not be economically feasible to do that. We're going to look at how to actually come up with that number in a little bit. Yeah.
Back to the
Yeah.
page with the-
I was going to.
Filter 99%, you add, subtract more than like 95. Because it's only 4% in between 95 and 99.
Yep.
But numbers seem to be being further apart.
Because look, this right here and this right here, it starts to tail off. That steepness is no longer there. So that means it's going to be a wider number that's at the end there. So that's why the more accurate you get, the closer you try to get to 100%, the further those numbers are going to come apart. Okay. That's why the variety comes in. It's like in most situations, 95% is where we use. And almost all situations, we use 95%. When you start to look at medical situations and things that can come into life and death type situations, that's when we end up going to that 99%. Because we want to be extremely confident that that's going to be somewhere in there. Okay. So, but yeah, most times, most problems, 95% is where we're going to end up being at. Rarely do we ever use 80%. 90% is used quite often, but not as much as 95.
Yeah, I was just confused because like the top one,
Yeah.
it's like 30% or 30 different from each other. Like when you go 9 to 276, that's about 30. 30.
Yeah,
It came to like 95, 99.
yeah, it jumps quite a bit. All right. Try this one. Okay, don't type the numbers in there. Okay. So you got your two.
Yeah.
You're changing the use of the control. So you were missing X.
Yeah. Mhm.
You have X,
Those are the numbers that you have.
right, which you're missing. So first of all, change that to an S.
Mhm.
No, that's
Well,
X. The next one isn't S. You use S, not a.
Mm.
They have to match.
Yes. Okay.
And so we now have S,
Mhm.
we have X, we have Z,
Okay.
and we don't have Z. So you need the Z.
Mhm.
So go above. Go above the X. Oh, it's not that much. All right, that's. We'll put yours in there. Equals. 1.645. So that was 90%. That was the last one I asked you to do.
Mm.
And there's your two numbers. See how it calculates it for you? Now, what I want you to do is look at this problem and fill in your four numbers. All you need to find is your X, your N, your standard deviation, and your Z. And then the calculation will come out for you. Huh? Yes, N is the sample. It'll be back in a second. It kicked me out. There. Uh, 95%, right?
So the standard deviation, not the O.
Well, it's O, but it's not an O. It's that funky omega. But I didn't want to use the. You can't put that symbol in there easily, so I just used S for standard deviation because that's. I use the English letter for it instead. It makes your life a little easier. So in this case, your S is right. Technically, you can use any letter you want. You could have used O. You just had to make sure in your formula you used O instead of S. It wouldn't have mattered. All right. So I put in X is 147.58. Z is 196 because it was 95%. That's from that table. S was 13.25 and N was 100. There. So random sample of 100. Standard deviation. Sample mean 95%, which is 1.96 based on the table. Yes. Then you, oh yeah, you're going to. The little triangles are there because it can't calculate it. So like if I take away the X here, you notice it gives me the little triangles.
Oh, okay. So you have-
It won't give you that until you fill in the numbers.
Okay.
Yeah. Yeah, it won't put anything there until once you fill in all the numbers and that will because it's an error symbol. It's like something's wrong.
Yeah.
So that means that the actual mean where the ball will burst is somewhere between 144.98 and 150.18. And I'm 95% confident somewhere in there.
Why are these values so good compared to the last time?
Standard deviation is a lot smaller. Last one standard deviation was 900. Remember, a bigger standard deviation means a wider range, right? This one, my standard deviation is 13.25, so it's a lot smaller in respect. So if I'm going to stamp my soccer ball with don't inflate higher than this, what number should I put on the soccer ball? I'd probably do 145, be on the low end.
Where did you get the 1.96?
Look at the table that you wrote down.
Oh,
What was 95% equal to? So now you can start to see how they can use this to actually do real life situations. So they'll test 100 balls. And like, okay, it's 147. That's there. I know my standard deviations around this, so we're going to stamp the low end so this way they don't blow up on people. Okay. Don't overinflate higher than this, for example. All right, so we started talking about when we're looking at the engine one or even the soccer ball one that we have that range. It's like, let's see, how do I figure out what my sample size is going to be to get what I want out? So if you're going to sell boxes of cereal or any product, if a box of cereal says 16 ounces on it, does it have exactly 16 ounces of stuff in it? No. It's going to be a little higher, a little lower. It depends on how it's filled, but it should be the mean of a certain number of them should be 16. Okay. Don't think about the air. That's the way it's packaged. It's still 16 ounces in there. If you actually open it up and weigh it, it'll be around 16 ounces. It'll be close. So when they want to figure out if they're within that range, they need to figure out how much their sample size is going to be to determine that. All right. So this company has 12-ounce bottles, and they want their error to be 0.05 ounces. Okay. So how large of a sample do they need to take to be 95% confident that their machines are within 0.05 ounces in that bottle? Oh, I didn't switch over. That would be why. Okay. So that's what the formula is going to be that's above it. In essence, it's a change of your formula that you just had with the Z's. We're solving for n, which makes my life a little more complicated, but here's a formula of sorts, so you don't have to actually do all the algebra. Yeah. Yep. So it is n equals z times your standard deviation over whatever your error is going to be squared. Okay. Again, this is the formula. You write the formula down. We're going to type it into decimals to get the answer. That z is exactly the same z that we were using before, based on the table. So 95% is going to be 1.96 or whatever it happens to be. Standard deviation, they got to give it to you. And the error is what they're looking for. So in this case, they're looking for 0.05. So for this formula, it is z. So 95% is what for z? 1.96 times standard deviation, which is 0.3, over my error, 0.05, and I'm squaring. Okay? I'm going to switch over to Desmos, so I'm going to type this in. When you're doing Desmos, a couple little tricks to make your life easy. Put your parentheses first of your parentheses, and then hit division. So you have the division already there. It's easier than trying to get the division afterwards. And now we're just going to type the stuff on the top and the stuff on the bottom. So 1.96 times 0.3. And on the bottom was 0.05.
So like break out the letters.
You can, if you're going to do a bunch of them, yeah, I'm only going to do one of these. So yeah, you can type in the formula and do the exact same thing you were doing before.
And if I leave like the other.
It won't matter. You'll just have to add E for error.
Yep.
And then it's going to use those same letters. So yes, you can do it that way. Since I'm only going to do one of these, I didn't feel like typing the formula in. And then we close the parenthesis and we square it.
How did you do your square?
A squared.
And then- oh.
That gives you the answer.
That's good.
Nope, it's just there. So 138.2976. Okay, so how many people or how many bottles do I have to sample to get my 0.05 ounce?
100.
Okay. Since this is a minimum error, this is the error that I want, right? If I went down, so by rounding rules, this would be 138. Okay. But that means I'm on the low end and my error might not hit the 0.05. I might be a little higher than that. So in these situations, when you're doing your error, you always round up. Okay. So we're going to do 139. You always want to error on the side of bigger than smaller. Okay. So, and since we're looking at items, you can't have a point of an item. So you're always going to round up to the next whole number. So in this case, we're going to look at 139 bottles. Does that make sense? So in essence, this formula here is just that for the confidence interval formula just solved for n. It's just easier for us to actually look at that as a formula instead of constantly solving for it. Okay. All right. Suppose a sample of 410 random selected radio listeners revealed that 48 listened to WXQI. Find 95% confidence interval for the proportion of radio listeners that listen to WXQI. All right. What kind of problem is this? What am I looking for? Huh? No. Okay, what's the question asking me to find? Confidence interval, okay? We've been doing those. Good. So for my confidence interval, for the ones that we've looked at so far, I need to know my mean, I need to know my standard deviation, I need to know my n, and I need to know my z, right? Okay. Is this a mean problem? They don't give me my mean, right? What type of problem did they say? It's a confidence interval for a what? A proportion. So this is those proportion problems. So this isn't a mean, this is a p. This is a p hat. So this is that p hat. So what is my proportion that they gave me? It's 48 out of 410. And if you divide that, you get 0.1171. I did this last class, so I know the answer. It helps to do the same lesson twice in one day. All right, so that's my proportion. Okay. What's my N? 410. What's my Z? 1.96, because 95%. What's my standard deviation? No, that's my proportion. They don't give it to me, right? What's the formula for a proportion for standard deviation? We did this in chapter 8 and 9, I think. That's the formula. So remember, we're not changing those formulas. Those formulas that we used before are still being used. Okay, so in this case, we've got the square root of 0.1171, 1 minus 1171 over 410. So square root, division, so we got 0.0159. Oh, did I just literally erased everything I had there? Oh, nice. Okay. Let's type that again. I think I didn't need the rest of it. All right. Now we need to find our confidence interval, right? Think back to what we just did for our mean. It was my mean plus or minus the calculation, right? And this one is going to be my proportion plus or minus. So it's my proportion plus or minus the z. Now this one, we only have to multiply it by its standard deviation. We don't have to divide by the square root of n because we already did the square root of n in it. Okay, we already have the square root of n done within my standard deviation, so I don't have to do that extra piece. So it would be 0.1171 plus or minus 1.96 times 0.0159. That'll be all your proportion problems. Yeah.
So that's your answer right there.
Well, I have to do it, but yes. So another nice little thing, you can do this on your computer. I don't know of an easy way to do it on your phone. You type it in once, you can copy and paste it and just change the plus sign.
You just do plus?
Yeah.
Oh, you have to do it twice.
Yeah, you do the minus and the plus. You can't do both. It won't do both. But all I did is I just copy and pasted it and then just change that to a plus to make your life a little easier. So we're between 0.085 and 0.148 is the actual proportion of people who listen to the radio, this radio station. So after they did a sample of 410 people, they thought it was around 11%, but that's what they got from the sample, but it could be anywhere from 8.5% to just about 15% in reality. Okay. No, this formula is not much more complicated. It's just, we just didn't have to divide by the square root of n because we already did it in my standard deviation. All right.
I have a question.
Yes.
So, like in the previous problems, would they already give you your standard deviation? Like, is that standard deviation found in that formula?
So, okay. So they will never give you your standard deviation when you're doing a proportion. They will only give you your standard deviation when you're doing a mean problem. So that's why we have to divide by the square root of n, because we do that in the calculation for it. In our proportion problems, we have to find our standard deviation, so that you have to do that calculation. All right. Now, when we're looking at a lot of our situations, a lot of them come down to a proportion. That's that binomial. It's a this or that type of situation, right? So when we're looking at our formula for error, this one actually becomes way more useful and actually way more common to use. So if you remember, we were talking about like polls for the presidential election, stuff like that. What was the percent that I always said they always had? It's plus or minus something. 3. That's their error. Okay, so they set their error before they actually set how many they're going to talk to. All right, so they're saying, okay, I want an error plus or minus 3%. How many people do I need to call to hit that error? This is what they're doing. This is the formula for it. Notice, this formula has nothing to do with anything except for what the proportion they have is. In most of those situations, they assume the proportion is 50-50. So if we're looking at this formula here, so we'll use our 95%, so 1.96. I know, I'm using the formula that's right there. So Z is 1.96. I'm going to show you the Desmos in a second. And then my proportion is going to be 50%, so 0.5. And then I do 1 minus 0.5. And I want my error as 3%. So what's that going to be as a 0.03? Okay. Oh, I forgot the squares. Squared. Squared. Okay. If I type that formula in, there's my formula. Notice 1.96 squared, 0.5, 1 minus 0.5, 0.03 squared.
Why isn't all of that in like see like we did?
Because the whole thing is in parentheses in this look at the equation. The whole thing is in parentheses. So I didn't put the whole thing in parentheses because the whole thing's not in parentheses. How many people do they have to talk to? 1,067. What number did I kept telling you that how many people they have to talk to figure this out? About 1,000. That's where that number came from. So notice, is my population anywhere in this situation? No. So I don't care if my population is 350 million or 700,000. You have to talk to 1,000 people to get a plus or minus 3% error. Okay? Crazy, isn't it? Anybody ever have their favorite TV show canceled? Happens less now than it used to because of all the streaming services. It used to be you had Nielsen families. So Nielsen is the company that looks at all this data and everything else and determines if a TV show is good or not. And what they used to do, this was pre-internet in essence, they would send boxes that you'd plug into your TV, into your cable, or into your antenna. You plug it into your computer at there. They'd send out 500 of these boxes to 500 homes around the country, 500 total. And when they were sitting down to watch TV, they would press a button to tell which person was watching that TV at that time. And each number on the TV, so let's say it's a standard family, there's 4 people at the house. Each one was assigned a number, so this way they knew the demographics. So if it was the man watching it, the woman, or the 12-year-old kid, or whatever else. And based on that, based on those 500 homes, they determined if a show is good or not. Should it stay on? Is the advertiser going to spend money on it or whatnot? That's it. So they basically asked 2,000 people in the entire country to determine what everybody's going to watch. When the internet and stuff like that and streaming services became more popular, they have more demographic information that way. But Nielsen actually they used to send out a little box that would listen. And each show would actually have like a tone that the box would pick up. And that would register what you were watching and would know when you were switching and whatnot. So same concept that they were using. But that's all the data that they had to determine this. So when we start to think about when we make these decisions and these calls, we're looking at very few numbers of people to make a decision on what's going on. And this formula is the one that they use to do those calculations. So pretty much all your statistics is based off of this formula right here on how many people they need to talk to. If they wanted a smaller error, we wanted like a 1% error, we'd have to talk to more people. Say we didn't care, we only wanted a 5% error. Oh, I got to talk to 384 people. So you can start to see how they've settled on a specific number that's useful enough. And anything within 3%, they call a statistical tie because they don't know where that actual number really truly is. Somewhere in between there, they just don't know where. So if it's 5%, that means it could be anywhere from 0.47 to 0.53, 47% to 53%. I don't know, somewhere in there. And it really doesn't make that big of a difference if we're talking about at 4%. That doesn't change too much. So even if this changes up here, the big thing is that number down the bottom. That's the thing that really changes how many people you need to talk to. All right. So the radio station wants to have an error of 0.1%, or sorry, 1%, not 0.1%, 1%, with a confidence interval of 95%. And we already know the proportions 0.1171 because we just did this problem. So we would go back to our Desmos. That stays. This goes to 1%. And this is 0.1171. So they need to talk to 3,972. Remember, always round up. People. Could we have their actual percentage somewhere in that 1% range? You actually cannot do any of the lessons for homework yet in chapter 10.
Yeah.
You cannot do any of the homework in chapter 10 yet because I've only covered half the sections. I covered half of section 10.2 and half of section 10.3 because the only thing we haven't done is we didn't do I don't know the standard deviation ones. So we have to look at a different table for that. And I didn't print out the table because I forgot. So I will have those on Wednesday and we'll go over that lesson. on Wednesday. All right. Any questions? Okay. Then we're good. I will see you on Wednesday.